Now we'll start with one of the most important topics that of linear programming, which is the simplex method, solution of linear programming problems by simplex method. What we'll do, we'll mix theory and problem solving to understand. If I go by theory only, you won't understand, or I start solving question, you won't understand. So what I'll do, I'll mix theory and solution, problem solving technique. Now you have seen graphical method. In graphical method, it was like this. Let's say this was the feasible region where we had feasible solution. So we had 1, 2, 3, 4. Let's say O, A, B, C. We have 4 vertices here. So in graphical method, we saw that optimization is possible on the vertices only of the bounded feasible region. This is bounded. So we have maxima and minima, or the optimal maximization and minimization at vertices only. In case of unbounded also we have seen the theorem that if it exists on the vertices only. So in simplex method, the idea is that we reduce the infinite number of solutions to a certain number of solutions. How? Try to understand the first part. Let's say we have m number of constants. M is the number of constraints, and the number of variables is, let's say, m plus n. What is the meaning of this? x1 plus 2, x2 plus 3, x3 is equal to 7. 2x1 plus 3, x2 plus 4, x3 is 11. So we have two constants given here, that is m is equal to 2, but the number of variables is 3. So m plus n is 3. So this is the first thing to understand, m and m plus n. Now how we proceed? We proceed by putting n number of variables equal to 0. N number of variables equal to 0. That is, m plus n is 3 and m is 2. This means n is equal to 1. So we will put one variable equal to 0 and then see, for example, if we put x3 equal to 0, we will see what is the solution for x1 and x2. Then in the second step, we will put x2 equal to 0 and we will see what is the solution for x1 and x3. Then in the third step, we will put x1 equal to 0 and we will see what is the value of, or what is the solution for x2 and x3. Clear? This is the first part. Now, so when we put this n number of variables equal to 0, then this n number of variable is called non-basic variable. That is, in the first case, if we put x3 equal to 0, that is called non-basic variable. And the other two, which is not equal to 0, x1 and x2, they are called basic variables. Clear? If when we put x2 equal to 0, then this is non-basic variable and x1 and x3 is basic variable. Similarly, when we put x1 equal to 0, that is non-basic variable and these two are basic variables. Clear? So how many times we will have to do that, we can get by a simple expression, m plus n cm. So in this we get 3 c2. This is factorial 3, factorial 1, factorial 2. So this is equal to 3. So we'll have to repeat the process 3 times, as we just saw. We'll first of all, we'll put this one 0, then this one 0, and then this one. So we'll have 3 different possible solutions. Clear up to this? And one more term to be remembered is, if when we put this equal to 0 and we get the values for this and this, if they are positive, then the solution is non-degenerate. Otherwise, it is degenerate solution. Clear? That is, when putting one variable to 0, if the solution to these are positive, that is non-degenerate. But if it is not positive, it is degenerate solution. Okay? And from that, we'll see the value of the objective function. The value for which it is optimum is called optimal basic feasible solution, or simply optimal solution. This was the theory part that I had to tell. Now I'll start with an example and explain these things step by step. First of all, we are applying simplex method for equations, not for inequalities. So first of all, understand how to optimize equations. Okay, when the constraints are in equation form. Then later on we'll go into inequalities. We have two equations that are constraints. I am not giving any objective function to maximize or minimize. We'll just understand what are basic variables, what are non-basic variables, what is the meaning of feasible solution, what is the meaning of degenerate and all. So we'll construct a table to understand this. First is, this is a number of solutions. Second is, what is the basic variable here? Basic variable. And what is the non-basic variable? Non-basic variable. Then is the solution, then we will see the values of the basic variable. You understand what is basic variable? We'll just see. Now, there are two questions. First, is it feasible? Feasible means if the solution is feasible. Solution feasible means your x should be greater than equal to 0. And second is whether the solution is degenerate. Degenerate means that this should be non-negative. Let's see. Step by step we'll understand. We'll do mathematics here, so let's make it bigger. Okay. So first, or before that, let's understand one thing. Here we have m plus n, 1, 2, 3. Okay, that is the number of variables. I told you m plus n is the number of variables, and m, that is the number of constraints. We have 2. So 3C2 will have 3 numbers of basic solution. So first solution, what I told you, we will put one variable equal to 0. That will be non-basic variable. So let's start with non-basic variable x3. That is, we will put x3 equal to 0. Therefore, basic variables are x1 and x2. So when x3 is equal to 0, this equation will become 2x1 plus x2 equal to 11 and 3x1 plus x2 equal to 14. Clear? x3 is equal to 0. So what will be the solution? The solution will be, let's say, this minus this. So this will be x1, this minus this. x1, this is 0, 14 minus 11. So 3. So here we have the solution is x1 is equal to 3. And then what will be x2? x2 is 11 minus twice of this, 6. That is 5. x2 is equal to 5. Okay. So when x3 is equal to 0, that is when we have made x3 as a non-basic variable. The values of the basic variables are x1 equal to 3 and x2 equal to 5. So is the solution feasible? Yes, because these two are greater than equal to 0. Is this degenerate? No, not the solution is not degenerate because these are positives. Okay. Second will be, we'll make x1 or x2 and x3 as basic variable and x1 as non-basic variable, that is equal to 0. Now when x1 is equal to 0, we'll write x2 plus 4x3 is equal to 11. Then we have x2 plus 5x3 equal to 14. What will be the value? See, this minus this cancels. This is x3, so 14 minus 11, 3. So we have x3 equal to 3. x3 equal to 3. And what will be x2? x2 will be 11 minus 4 into this. That is 12. 4, 3, 12. So x2 is minus 1. Now, this is not feasible. This solution is not feasible. Why? Because our basic variable is negative. So no. And is this degenerate? Yes, it is degenerate because this is negative. Okay. So first is this, second is this. Let's see the third one. So third one will be when we have x1 and x1, x3. So x2, 0. So x1 and x3. So what will be the, let's write it here. When x2 is 0, our equation will be twice x1 plus 4x3 equal to 11 and thrice x1 plus 5x3 equal to 14. Okay. So what is the value? Let's multiply this by 3 by 2. So when you multiply this by 3 by 2, this becomes 3 by 2. So this becomes 6 and 33 by 2. Okay. and this minus this, that is minus x3 is equal to 14 minus 33 by 2. So this is 28 minus 33 by 2, that is minus 5 by 2. So x3 is here. So x3 is 5 by 2. Now when x3 is 5 by 2, thrice x1 is equal to 14 minus 5 into 5 by 2. So this is 28 minus 25 by 2. So what you get? 28 minus 3. So 3 cancel. X1 is half. So x1 is half. So again, this is feasible. The solution is feasible, and this is not degenerate. Okay. So this is the way we take basic variables, non-basic variables, and we see whether it is feasible or not. The most important thing to consider is that whether the variables that we are getting, that variable is positive or not. Now, in this only, this is what I had to explain. Now, in this only, if our objective function was, let's say, z was equal to 4x1 plus x2 plus 3x3. Now, let me make you understand. Let me explain to you how to maximize it, and we have to maximize it. Now, we have 3 sets of x1. In case of this, if we put x3 equal to 0 and this x1, that is 4 cross 3 plus x2, that is 5. So this is 12 plus 5, 7. So z will be here 12 plus 5, 17. Okay. This is the solution is not feasible. So here we won't take z. Here x3 5 by 2, x1 1 by 2. So z is, x2 is 0. So x1 is half. 4 into half, that is 2, plus we have x3. x3 is 3x3. So 3 into 5, that is 15 by 2. See, 3 into 5 by 2. This is 19 by 2. So our z here is 19 by 2. Obviously, you can see this and this value. This is maximization. So from here we can say that at x1 equal to 3, x2 equal to 5 and x3 equal to 0. At this vertex, we have the optimal solution for this objective function, which is equal to z equal to 17. Clear? We'll see one more example and we'll maximize the value. So that this is, we repeat this process and so everything gets clear. So we have z equal to this. We have to maximize it. The constraints are this equal to 4, this equal to 7, and these all are positive. So let's see how. The first will be the number of solutions. What will be the number of solutions? See, here also m plus n is 3 variables, and m is 2. We have 2 constraints. So this will be m plus n c m equal to 3. So we'll have 3 solutions. Okay. So this will be the number of solutions. Then we'll have basic variable. What are the basic variables? And then we'll have non-basic variables. Then we have values of basic variables. Okay. Then is it feasible? That is whether all the variables are positive. And finally we'll see what is the value of z. Value of z. Okay. So what I'm doing is, let's give some space to this value of z. And is it feasible or not? Let's put it here. Okay, because the most will need more space in this column only. Okay, clear? x1, x2, x3. Let's put x3 as non-basic variable, that is equal to 0. So we'll have basic variable x1 and x2. So the equations will be x3 is 0. So this will be x1 plus 3, x1 plus 2. x1 plus 2 x2 is equal to 4, and 2x1 plus 3x2 is equal to 7. Okay. So what do we do? 2, 4, 8. Okay. And this minus this. So this is 4 minus 3. So this is x2 and this is 8 minus 7. So 1. So when this is x2 is 1, our x1 will be, we had x1 equal to, this was 4. So 4 minus 2x2. So this is 2. Okay. So x1 is 2, x2 is 1. So I'm writing it here. x1 is equal to 2 and x2 is equal to 1. This is the first basic variable. Obviously this is feasible. What will be the value of z? x3 is 0. Z is here. So see, 2 plus 3, that is z is 5 here. Okay. Now the second one, x2, x3, these are basic variables, so we'll take x1 as non-basic variable 0. So the equation will be x1 is 0 here, so 2x2 plus 3x3 is equal to 4, and 3x2 plus 5x3 is equal to 7. Okay. So what can we do? Let's multiply this by 3 by 2. So this becomes 3 by 2. So this will be 3. 3 by 2. So this will be 9 by 2. 3 by 2. So this will be 6. Okay. Now this minus this, or this minus this. This is 5. This is 9 by 2. So this will be half of x3. And this is 7 minus 6. That is 1. So x3 is 2. And what will be the value of x3? So we have x2. So thrice x2 is 7 minus 5 into x3. 5 into x3 is 10. So this is minus 3. So x2 is minus 1. So here we have x2 equal to minus 1 and x3 is equal to 2. This is not feasible solution. So this is not a feasible solution. So we won't find the value of z. Now the third solution. We'll have x1 and x3. And here x2 will be our non-basic variable. So the equations will be x1 and x3. x2 is 0. So x1 plus 3x3 equal to 4. Then we have twice x1 plus 5x3 equal to 7. So let's multiply it. 2, 6, 8. Okay. Now this minus this is x3. This minus this is 1. So x3 is equal to 1. This is the first part. Second is, it was x1 is equal to 4 minus 3x3. So this is 1. Okay. So x1 and x3 both are equal to, so x1 is 1, x3 is 1. Yes, it is feasible. And what will be the value of 1? x1 and x3, 1, 1. And this is 0. So this is 1 plus 3. So this is 4. So which is the optimal solution? This. That is z equal to 5 at x1 equal to 1, x2 equal to 0 and x3 equal to 1. This is the solution. Okay.